Hey guys, welcome to Safi Mixed. In this video, I want to find a solution to this problem of two pulleys in three masses. The solution to this problem means that I want to find the relations for acceleration in terms of the three masses involved and the acceleration due to gravity. Obviously it is working under gravity, and similarly I want to find the tension in the string in terms at this position and at this position in term of the two masses and acceleration due to gravity. And for that I consider I approximate our system in such a way that we assume that the string at this position is massless and inextensible. Similarly, we consider that the pulley P1 and P2, both the pulleys are massless and frictionless. So if they are massless, so if the strings are inextensible, that means the acceleration to on both sides of this pulley and on both sides of this pulley is same in the branches. And similarly, if the pulley is massless, mean its moment of inertia is zero, and when the moment of inertia is zero, that means the two pulleys just the two pulleys just change the direction of tension on both sides, for example, and the magnitude of the tension on both sides are same. That is, the tension at this position is then exactly equal to at this position, and similarly the tension in this branch is exactly equal to the tension in this branch. So although I have designated, although I have put a subscript over there, but this tension must be the same. So our assumption says that T naught at this position must be equal to at this position, T1 and T2 must be equals. And then if that's the case, let me represent the weights. The weight of this is M1G acting in the downward direction, and of this mass is M2G acting in the downward direction. Now, since this tension is supporting these two tensions, therefore, from this geometry, we see that T naught must be equal to T1 plus T2. That is, the first equation that I establish is this one: T naught equals T1 plus T2 and magnitudes. Obviously, this is since the pulley is frictionless and massless, therefore this tension is equal to this tension, and I use the notation T for them. So I write this as T plus T equals 2T, which means that the tension at this position or this position is twice of the tension either in this branch or in this branch. And now, if I focus only on this mass, there is only one force acting on it, and that is T naught, and this force is producing acceleration. We further consider that the acceleration that the surface on which M is placed is totally frictionless, so no friction is there in between the mass and the surface. Under that condition, the only force acting on mass M is T naught, and according to Newton's second law, we have T naught would be equal to MA. I'm not putting vectors because A and T are in the same direction. That is just a scalar equation then. And from this, I can write that that 2T equals. So if I use this value, that means I can write 2T equals M times A, or T equals half M times A. I put this equation, I write this equation over here because I'll be using this later on, so I want to note this over here, MA, and I call this equation 1. Okay, that is one. That is for mass M1. Now we have another situation. I don't need these equations, so I set things to that equation, therefore I can remove them easily. Now look, what do we have? if this mass is very, very large, then the sum of these two masses, then the system would be stationary. There will be no acceleration. And if this mass is not there, if this mass is zero, this would be a free fall. We will see these conclusions from what we derive next. But the forces acting on M1 are M1G and T1, and the forces acting on M2 are M2G and T2. And with respect to this pulley, these masses has one kind of acceleration, and with respect to this pulley, these masses has another kind of acceleration. So we can say, since this pulley is stationary, this is movable because it moves up and down as the mass moves in this direction. Now, with respect to ground, the acceleration in this mass and the acceleration in this mass are, we can take even pulley 1, that doesn't make any difference, has two branches. One acceleration with respect to this pulley and the other acceleration due to the whole system. So if I write the net force on M1 and I consider the downward direction to be positive, then I can write M1G minus T1. This must be equal to M1 times the acceleration of mass M1. And I write that as A1. And similarly, M2G minus T2, this is the net force acting mass T2, and according to second law, this must be equal to M2 times A2. Now, the net acceleration A1 and A2 in this mass must be the sum of acceleration at this part and the sum of acceleration with respect to this pulley. Let the acceleration with respect to this pulley be A2 prime in this, and with respect to this will be A1 prime. Then the net acceleration in this mass and in this mass would be the vector sum of two accelerations. That is, A1 would then be equal to A1 prime plus A. This one acceleration at this position. And similarly, A2 would be equal to A2 prime plus A. And obviously this string is inextensible. This acceleration in magnitude is exactly equal to this acceleration, but if this mass is moving downward, then this would be moving upward. And similarly, if this is moving downward, this would be moving upward. They are opposite in directions, so we have this condition. A1 prime is equal to minus A2 prime. This is the condition, because if I consider M1 is moving in the downward direction, this would be positive, that one would be negative. Or from this I can write that A1 prime plus A2 prime is equal to 0. This is vector sum. So if I add up these two equations, I can write A1 plus A2 equals A1 prime plus A2 prime plus 2 times A. And A1 prime plus A2 prime equals 0. So this thing in fact reduces to A1 plus A2 equals 2A. Okay? And since all these accelerations are along a straight line, therefore we can write this in a scalar form. A1 plus A2 equals 2 times A. And I write this, let me call this equation 2, this equation 3, and this equation 4. So I write equation 4 over here. A1 plus A2 equals 2 times A, and I call this equation 4. Now, let me arrange. I don't need this even, so I noted the net result of this algebra, vector algebra, so I need to now I divide equation 2 with M1, and that if I do, and I invert the whole of the equation, from that I can write A1 equals G minus T1 divided by M1, and I divide equation 3 with M2 and invert it, then I write A2 equals G minus T2 divided by M2. And now I add these two equations. If I add them, I can write A1 plus A2 equals 2G minus, since T1 equals T2 and I have already used the notation T for them, I can write that as T, and similarly I can write T2 as T, and can take T common from these two terms, write this as 1 over M1 plus 1 over M2. And now if I compare this equation with equation 4, I can write 2 times A equals 2G minus T, and I'm putting this, taking LCM into the form M1 plus M2 divided by M1, M2. And from this I can find the value of T, and that I do like this: minus T into M1 plus M2 divided by M1, M2 equals 2 times A minus G, or if I take this to this side, and then I'll get G minus A. So finally I can write T equals 2 times G minus A into M1, M2 divided by M1 plus M2. Okay, this equation gives me the tension in terms of acceleration A of mass this or of this pulley. And I want to note this equation somewhere. Let me write this equation at this position, because I may need this equation later on. So I write this as T. I call this equation 5, and I write this over here. So this is equation 5. I call this one equation 5, and I note this at this position. I will need this 2 times G minus A into M1, M2 divided by M1 plus M2. This is not a complete equation, because this is equation 5. Let me call this equation 5. This is not, because we have an unknown A over here. We haven't yet find the value of A, so we cannot get any better information from this equation. We first need to find A for this equation. Now, if I compare equation 5 with equation 1, I again don't need any of these things, so I can safely run them. Okay, if I compare this equation with this equation, then I can write half MA equals 2 into G minus A into M1, M2 divided by M1 plus M2. And now I can find the value of acceleration A from this equation. I can do that by taking this part of the acceleration to this side. So first I multiply 2 with the 2 equation. This will cancel 2 with this, making this 4. And I can then write M. And this would be minus 4A. If I take that minus 4 to this side, that will become plus. So I'll be writing this as 4 into M1, M2 divided by M1 plus M2, the whole multiplied with A. And this would be equal to 4 M1, M2 divided by M1 plus M2 times G. Okay, I can read that equation into this form. Let me check, am I doing correct? So I first multiply with 2, this would become m, this would become 4, so I'll have 4a into this thing, and if I take it to this side, yes, that is correct. And now I take LCM of this part, so it would give me m into m1 plus m2 plus 4 m1 m2 divided by m1 plus m2 and multiplied with a, and this equal to 4 m1 m2 divided by m1 plus m2 multiplied with g. Since we have the same denominator on both sides of the equation, therefore I cancel that with this. And now I can take this thing to that side of the equation and can write for acceleration the final relation in the form 4 m1 m2 whole, this divided with this, so I write this as 4 m1 m2 plus m into m1 plus m2, and this whole multiplied with g. Yes, now this is the equation for acceleration. I call this equation 6. This equation defines the acceleration A of this mass or of this pulley, and it is in terms of the already known quantities, that is m1, m2, m, and g. So this is a very good equation. Now let us analyze this equation. If we set m equal to 0, that is, there is no mass at this position, so this term would be equal to 0, and we will be left with the numerator exactly equal to denominator. That will cancel with this, and we will be left with a equals g. Mean this pulley will be dropping, will be moving freely with acceleration g, so that would then be a free fall, and that's obviously the case because this is frictionless. If I cut this string somewhere at this position or this position, everything will be moving down with this acceleration. On the other hand, if m is very very large, that m1 plus m2, we want this condition to look, what would we have? If the mass m is very very large, then the sum of m1 plus m2, then what would we have? This thing would be equal to, then we would have 4 m1 m2 plus m time m1 plus m2 approximately equal to m. That would have no much contribution with this thing, and under that case 4 m1 over m2 divided by m would be approximately equal to 0. This approximation would then lead to a equals 0, and that is what we see in our common life. If this mass is very very large, this is a very heavy body, then there will be no acceleration in any part of the system. So we retrieve the same observation from our equation. Now I can use this value of acceleration at this position in equation 1 to find t. So that I can do by putting t equals half m into the value of acceleration, which is 4 m1 m2 this whole divided with 4 m1 m2 plus m into m1 plus m2 and the whole with g. I can cancel this 2 to give me 2, and then I can write 2 m m1 m2. I multiplied this m1 with that, and I get 4 m1 m2 plus m times m1 plus m2 the whole multiplied with G. And we can again see that if M is 0, means there is no mass, the numerator of this equation goes to 0, and if this goes to 0, there will be no tension. So, and that's what we observe in our common life. That is, if this mass is 0, there will be no tension. Again, this will be a free fall if this is allowed to fall. So we have the same observation. Now we can use the value of acceleration the value of tension T to find acceleration A1. So I don't need this. I want to use this value of T in this equation because, okay, from this we can find, since we learned that T naught equals 2T. So if I multiply this with 2, this is T naught. That was, I started with T naught equal to 2T, so T naught would be twice of this value, so we would have a 4 at this position, means the tension in this region and in this region would be 2 times the tension in this region. So that's very simple, we can do that. Now, if I put, since T1 and T2 are equal and we have set that equal to T, therefore I can replace the value, this value at this position. I can call this an equation 7. So equation 7 gives the tension at this position and this position. And if I put the value at this position, I can write acceleration M1 equals G minus 1 over M1 times T, and I put the value of T, so that would become 2M M1 M2 divided with 4 M1 M2 plus M times M1 plus M2 and the whole multiplied with G. I can cancel this M1 with this M1, and now I can take G common from this in this term and can take LCM. So I do that directly. If I multiply this over here, it will give me 4 M1 M2 plus M, and I open this bracket at this. Let me write it as it is: M1 plus M2, and then minus 2M M2, and this whole divided with this thing 4 M1 M2 plus M times M1 plus M2 multiplied with G. Okay, if I open this bracket, I would have M times M2 and M times M1, and that M times M2 minus 2M times M1 will give me minus M times M1. So I want to write the final relation at this position. I don't need these, so I would remove them. I can write M1 equals 4 times M1 M2 plus M M1, and MM2 minus 2 MM2 is minus M M2 divided by this thing 4 M1 M2 plus M into M1 plus M2, and this multiplied with G. Or one more step, I can write M1 equals 4 M1 M2 plus M. I can take M common from these two, and I write there M1 minus M2 divided by 4 M1 M2 plus M into plus M2 times G. And now see, and obviously A2 we have already seen that is equal to minus A1. and the same magnitude both acceleration have. Now, one thing more we need to look into this equation. If m is 0, then this term goes to 0, this term goes to 0, that is one term numerator and denominator diminishes. We will be left with 4m1 m2 divided by 4m1 m2. They cancel with each other, so a1 equals g. Means if we break the string or this thing is 0, these two, both the masses will move with acceleration g. Means the whole of this system would then behave as a free fall, and under that case the tension in this string must be equal to the tension in this string and must be equal to 0. So there will be no tension on these on these sides of the pulley. So everything is a free fall then. So this way we solve a system of two pulleys like this one. And thanks for watching.